eraser. Okay, today I'm going to talk to you about a small chromitite layer that was found in the Kevitsa deposit that is enriched in platinum group minerals. And I will show you the model, the genetic model that we have proposed. Okay, just very quickly, chromites are important because they are usually enriched in chromium. They are the main source of chromium, and they are usually enriched in platinum group elements. Chromitites are usually found in both layered intrusion and ophiolites, but from a crystallized mafic magma, they form only 1 or even less % in volume. So we need an external process to reach the chromite-only saturation of the system. So there are several models proposed, but I just want to focus on that propose the contamination of mafic magma with some silica component to reach the chromite-only saturation. Okay, just some geological context. Kevitsa intrusion is a ultramafic late intrusion of 2,058 million years old. Sorry, that is located in the central Lapland Greenstone Belt in northern Finland, and that hosts a nickel-copper-PGE deposit. The intrusion is hosted by some black skis and mica skis with some sulfide and graphite contents, as well as some mafic ultramafic metavolcanic rocks. It's common to find xenoliths of both skis and ultramafic rocks in the whole intrusion. From the bottom to the top, the intrusion is made up of an ultramafic unit at the bottom. Then we have a gabbroic unit and a granophyric unit at the top. If you take a look to the core draw here, to the drill core section, you will see that the mineralization is hosted in the ultramafic unit. Okay. This unit is basically made of olivine pyroxenites and pyroxenite with olivine decreasing upwards, and some pyroxenites have peridotite bodies. There are several styles of mineralization depending on nickel tenors, but basically they are dissemination of nickel copper sulfides with some platinum and palladium contents. In the upper part of the intrusion, there are some platinum group element rich levels with gold, and about 30 meters above one of these levels, we found the chromitite layer on this study. Okay, the chromitite is here is a massive to semi-massive body composed of chromite grains with mineral ilmenites and platinum group minerals. Some sulfides can be found also, but it's a minor phase. The intercumulus minerals are mainly biotite, amphibole. The body is hosted in pyroxenite with both OPX and CPX, but there is a mineralogical variation between the hosted rock, below and above the chromitite. So biotite is more common upwards, and plagioclase with albite composition came after. Also, there is a compositional variation in pyroxenes below and above. So you can see here in the yellow circle, sorry, there is an enrichment upwards in calcium, sodium, aluminium, and phosphorus. Also, there are some composite inclusions in chromite, including amphibole, titanite, and chlorides, as well as biotite. So somehow, we suggest that there is some kind of addition of these elements to the melt during the chromite formation. Regarding the chromite chemistry, we see that they are quite rich in chromium, but they are extremely poor in magnesium. So they plot very far away from the typical composition of chromite in light intrusion stratiform chromitite. This could be ascribed to metamorphism. Actually, we have seen some magnetite rims around chromite that suggest metamorphism, grain case phases. But we did some analysis from core to the rim of chromite grains, metamorphism, but we didn't see variation in chromium number. and neither in magnesium, just some variation from core to the ring and some decreasement in iron 3. We scanned the whole chromitite layer to check the amount of platinum group minerals, and we found a total of 37 platinum group minerals. The most common is perilite, then laurite, and then earosite, but there's also other ruthenium and rhodium-bearing platinum group minerals. If you take a look to the picture, you can see that there is two different positions where the platinum group minerals occur. So you can find them attached to the oxides, mainly chromite. You can see here that. Or they can come up as intergranular grains hosted by silicates. Also, there is a connection between the position, the textural position, and the composition of the grains. So those grains attached to the chromite boundary are mainly laurite and earosite, whereas the platinum-bearing minerals are mainly, of course, mainly as intergranular grains. So with all that features, we propose a model that assumes that there are some silica addition to the system because of the assimilation of xenolite. So this displays or moves the composition of the melt to chromite saturation only. During the formation or crystallization of chromite grains, the addition to trivalent cations to the grain promotes creates like reduced area around the chromite, promoting the crystallization of platinum group mineral attached to his boundary. So the intercumulus melt become enriched, relatively enriched in platinum, especially in platinum and palladium. So the intergranular perilite crystallize, and then during the silicate growth, these platinum group minerals are trapped by these silicates. So as a conclusion, we could say that the chromite saturation of the system was probably reached by the assimilation of the xenolite. We can see that also some other elements as calcium and sodium were added in the compositional variation of the pyroxenes. We can say that sulfide segregation didn't play an important role in collection PGEs because we didn't see almost no sulfide minerals hosting these platinum group minerals. The heterogeneity distribution of the platinum group minerals suggests different behavior of both PPGE and IPGE. So ruthenium and iridium-bearing PGMs were formed by the variation of oxygen fugacity on chromite grains, whereas the platinum group minerals formed from the hybrid melt with no sulfur participation. So some questions are still unsolved, like being a mineralization of platinum group elements below the chromitite, where these platinum group elements came from, as well as which is the detailed nature of the xenolite and its composition, and why there is no more chromitites similar to that in the Kevitsa intrusion. Just if you want more information about that, you can see all the data here in this paper published in Mineralogy and Petrology Review. So thank you.